Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning. It's my pleasure to introduce Zach Anderson. He's here interviewing for a postdoc position. He's in graduate school at Berkeley, working with Eric Brewer, keeping the world safe from buggy systems programmers like me. Thanks.
Thanks, Ed. Right, so as Ed said, I'm here from the University of California, Berkeley. My advisor is Eric Brewer, and today I'm going to talk about a compiler I've been working on for safe and efficient C programming. But first, I'd like to tell you a little bit about myself. I'm originally from Pittsburgh, Pennsylvania, and I stayed there to do an undergraduate degree in computer science. And after that, I moved to Berkeley to work on a PhD with my advisor, Eric Brewer, and I'm interested in compilers and type systems and static and dynamic analysis for improving software quality and safety, and also in language features for aiding concurrent programming and the application of all of these things to systems programming. And I'm also interested in building and releasing useful tools. So I've worked on a bunch of different things while at Berkeley. So when I started out as a grad student, I initially was working on Deputy, which was Jeremy Condon's dissertation work. And I wrote the optimization phase and improved some support for polymorphism and some other things. I also worked on Heapsafe, which is another project in the Ivy group, which checks calls to free by way of reference counting, and I extended it with some algorithms for the multithreaded case. And next, I worked on a project called Sharc, which is my dissertation work, and which I'll talk about in detail in this talk. I've also been working on something called atomic shelters, which is a pessimistic implementation of atomic sections for C, which is kind of like AutoLocker, if you know what that is, but it doesn't have it doesn't need whole program analysis to find a global lock order. I've also been working with the PAR lab at Berkeley in the OS group there, adding a variety of small features to Ivy to support their OS programming. And I've also been doing some more theoretical work with Meyer Naik at Intel Labs Berkeley, using data gathered from concrete runs of a program to construct an efficient heap abstraction for use in a subsequent static analysis. So in this talk, I'm going to give a brief overview of the design and some of the implementation of the Ivy compiler for C. I'll talk a little bit about the design rationale and the safety guarantees that it provides. In particular, I'm going to give an in-depth look at the concurrency checking part of Ivy, which is called Sharc. It's short for sharing checker. And I'll give a brief look, also give a brief look about how it supports shared pointer-based data structures. And finally, I'll show some results from applying Sharc to about 1.5 million lines of C code. So programming errors are a big problem. I probably don't need to talk about this in detail with this audience, so I'll just go straight through that. So the C programming language is widely used. I've even heard that people use it here at Microsoft. So people use it because it affords the programmer a lot of efficiency and control, and it's used to write a bunch of different system software, operating systems, database systems, web servers, compilers, and so forth. People also use it for applications programming. About 36% of the projects on SourceForge use at least a little bit of C. So C code is mostly correct. Over time, over the past 40 years or so, or whatever, programmers have developed a set of idioms for writing correct C code. That is things like, keep the length of the buffer nearby the pointer to the buffer, or protect a global variable with mutex, things like that. But C compilers don't really check that those idioms are followed. So in more modern languages, sometimes these idioms are strictly enforced, whereas in C they're simply conventions. But unfortunately, you probably can't take all of the C code there is and rewrite it in a modern language. And so part of the goal of the Ivy compiler is to develop an evolutionary pathway from C to a language with more modern features. That is, we want to allow programmers to improve the safety of their code, one modular, one compilation unit at a time, but also one safety property at a time. So we want to allow the programmer to declare the idiom, the C programming idiom that they're using, and then have our compiler check that they're actually using that idiom correctly. So the way we're doing this, our current approach is to add type qualifiers and some other small features to the language. And the reason is that even C programmers are at least a little familiar with types. And then we can do a little extra type checking, a little extra static analysis to make sure that the programmer is doing what he says he's doing. And we can use some dependent type qualifiers to express some richer properties if we need to. So the Ivy compiler currently has a few different parts, and I mentioned these tools before. So Deputy, Heapsafe, and Sharc. So Deputy enforces spatial memory safety. Heapsafe adds to that what we call temporal memory safety, and I'll say what I mean by that in a minute. And Sharc adds to those tools concurrency safety. And a bunch of people have been working on the Ivy project. People from Berkeley and Intel Labs. Berkeley. Yeah. So today I'm going to talk about Sharc. But first, I'll give a brief overview of the other parts. So Deputy enforces spatial memory safety. That is, it enforces that there aren't any out-of-bounds memory accesses in a program. So it works by allowing the programmer to add annotations on pointer types. So for example, here you can add an annotation on a function parameter, which is a pointer, saying how many elements are pointed to by buff. And the argument to the annotation, n, is another parameter to the function. And so Deputy allows you to write annotations like this on any pointer type in the program, in structures or variables or function parameters. So then, so Deputy also allows you to write annotations saying things like, this is a tagged union, this is an L-terminated array, and also it has some features for supporting polymorphism. So then Deputy will take a look at these annotations, and it will figure out what bounds checks need to be added to enforce these types at pointer arithmetic. And then we have a subsequent phase that goes through and looks at all of the assertions, and if it will always succeed, it takes it out. If it will always fail, it's a compile time error. And so Deputy, the checks that it does are sufficient to guarantee type safety, but only when the program is single-threaded and only when there aren't any dangling references. So that brings us to Heapsafe. So Heapsafe enforces temporal memory safety, by which I mean it enforces that there aren't any dangling references in a program. And it does this by way of reference counting. So we keep a 1-byte reference count for every 16 bytes of memory. And then when you call free on a pointer, you just check that pointer is the last reference to that region of memory. So when you're doing reference counting, you always have this problem with cycles. So Heapsafe deals with this by adding a couple of API calls, begin delayed freeze and end delayed freeze. And so the way this works is that after a begin delayed free, the runtime will keep a list of all the pointers that you free. And while you do this, it also goes through and it will null out all of the fields in the structure. And then at the end delayed free call, we do all the checking to make sure that you were really freeing the last references and actually free the objects then. So together, Deputy and Heapsafe can provide type safety and memory safety, but they're not sound for multi-threaded code. But that's sort of the case where you'd actually like to have a little extra help because the multi-threaded programming is a little bit more tricky. So this is where Sharc comes in. So the goal is to both capture the idioms that C programmers use to write multi-threaded programs, but also to fix the soundness problems in Deputy and Heapsafe. So just to review really quick, the common concurrency bugs. So you can have data races, which happen when two threads access the same location in memory, and one of them is a write, and there isn't any intervening synchronization. And this can lead to lost updates and other inconsistencies in state. But you can also have time of check versus time of use errors. For example, the state of the program could change after a deputy check, but before any subsequent point arithmetic that it was checking for. And you can also have deadlocks, but I'm not going to talk about deadlocks today. So concurrency bugs are a big problem. If you go and look in Bugzilla databases in major pieces of open source software, you can get the numbers. In particular, as of February, there were 62 outstanding known race conditions in the Linux kernel and 23 outstanding known race conditions in Firefox, and 30 outstanding known deadlocks in the Linux kernel, and 46 known outstanding deadlocks in Firefox. And these are just the known bugs, so there's probably a whole bunch more. So yeah, today I'm going to worry more about data races than deadlocks, but really these are sort of closely related problems. You might add extra locks to your program to get rid of a data race, but if you do that, you might introduce deadlock, and then you can then remove some locks, but then you might have another data race. So these are kind of closely related problems. But race freedom really isn't sufficient. So people have a strategy for writing correct concurrent programs, but a race detector doesn't really know what that strategy is. It tries to infer what is buggy behavior based on the memory access pattern in the program. So this could lead to both false positives and false negatives. So the contribution of Sharc is that we want to allow sharing of data among threads in a program only when the programmer intends. And the way that Sharc allows a programmer to do this is by allowing him to declare a high-level sharing strategy. That is, what is the sharing mode for a particular object in a program? And where does the sharing mode for an object change as a program runs? So Sharc will then use a combination of sound, static, and dynamic analysis to make sure that to enforce the sharing strategy that the programmer has declared, essentially, such that violations of the sharing strategy include what would otherwise be the real data races in the program. So we've also applied Sharc to a bunch of real programs, one of which is about 1 million lines of code. We've also run it on a couple of scientific codes with some interesting data structures. The runtime overhead on the scientific codes is about 40%, but generally the runtime overhead is under 20%.
So could you, 40% runtime overhead is kind of painful for scientific codes, but could you use this as a debugging tool?
Oh, yeah, certainly.
So you run it and is that how you intend to use it, or do you intend to deploy it with the overhead?
Well, I think it does, as you said, depend on what the application is. I think for scientific codes, it probably doesn't make a lot of sense. It probably does make more sense to use it as a debugging tool. And so we have we have a mode in Sharc that's just log and continue. So you can run the program, and it's slow, but you see all of the errors that you might have at the end. We also have a stop on error mode, which probably makes more sense when the runtime overhead is lower for some less compute-intensive application.
So is the slowdown fundamental, or do you think with you spent some time working on optimizations, you could reduce the slowdown significantly?
I think I could reduce the overhead. So at the moment, a lot of the runtime overhead for the scientific applications comes from maintaining the reference counts. And so these use a concurrent reference counting algorithm that requires each thread to keep a log of its updates. And then when some thread wants to know a particular reference count, it has to process the logs and then also update reference counts in a big global array off to the side. So I think there's definitely some work we could do at making the reference counting algorithm a little bit more cache friendly, among other things. Right, so I mentioned these sharing modes. So currently Sharc has these 6 sharing modes. So there's a private mode for objects that are accessible only to a single thread. There's a read-only mode for objects that are read by a thread but aren't writable. There's a lock sharing mode for objects that are accessible by a thread by only the thread that holds the lock. There's a dynamic mode, and this tells Sharc to check at runtime that an object is either private or read-only. We have a barrier sharing mode. It's like dynamic, but the checking resets at a barrier. And there's a racy mode for objects on which the programmer knows that there are benign data races.
What about interlock operations?
So I think that would definitely be a great addition to Sharc, but we don't currently implement any checking for that.
Really? All these codes you have don't use, because interlock is a very efficient way to avoid having to take locks.
Yeah, I mean, it certainly is. None of the benchmarks we looked at use those sorts of operations.
Wow. Microsoft code is absolutely full of them.
Oh, okay.
Okay.
So the sharing modes in Sharc are type qualifiers. So we have this declaration here, int read-only star private x. So this is a private pointer to read-only integer. So private here means that the variable x can only be accessed by the owning thread. And the read-only here means that the target of x can only be read. So we have a well-formless rule for how these types can be written. In particular, you can't have a non-private pointer to a private object. And so in the operations we're going to do coming up here, the key invariant is that all pointers to an object have to agree on that object's sharing mode. So I also mentioned on a previous slide a sharing strategy. So by sharing strategy, I mean a combination of the sharing modes in the program plus where in the program the sharing modes change. So for example, you could have a lock-protected counter or a queue or a cache, and you'd use the locked sharing mode. You could also have data that's initialized privately to one thread and then shared with everybody else in a read-only mode, and then the object would start out in the private mode and then switch to the read-only mode. You can also have objects transferred among threads by way of locks or signals. And so an object could start out private to one thread, then be put on some lock-protected queue, and then be taken off the queue by some other thread, and then it would be private to that thread. And you can also have lock-protected objects move between different lock-protected data structures. So an object might be in the lock mode with one lock, and then become private to some thread, and then go to being in the lock mode for some other lock. So in Sharc, the mode changes are expressed as typecasts, and I'll refer to them as sharing casts.
I have a question about the locked by list lock. So I can see that data structures may move, from one thread to another via a shared data structure like a queue or something like that, like producer-consumer pattern, right? So in here you say locked list lock. So while it's in the data structure, it's protected by the lock of that list. Is that what you're saying?
That could be, yeah. I mean, it depends on the program.
But I'm not sure how you would capture. How would you capture the producer-consumer example? For example, like you have a producer, and it's private to the producer. It goes into a list or a queue, say, and then the consumer takes it out of the queue. Which one of these patterns covers that?
The private to lock to private one. So I hold I don't know, some buffer, and then I write it with a sharing cast into the field of some queue structure that says it's protected by a lock. And then somebody wants to take it out of the queue, and so they'll do a sharing cast from the lock.
Rely on the queue to having a lock, being lock-based.
Well, I mean, if that's how it's implemented, then this is how you would express that. So now I'll give an example of the initialization case I just mentioned. So here we have a program that has a global variable config, and it's a buffer that's going to be read-only for all the threads. And we have a function called init, in which we allocate a buffer, initialize it privately to the thread, and then write the result into the global variable, and then start a bunch of threads that are going to share it. So if we were to fully annotate the program with Sharc's sharing modes, this is what it would look like. So the config pointer is a read-only pointer to some read-only data, and the local variable temp is a private pointer to private data. So there are a couple problems right now. So first is that we're initializing a global, we're initializing a read-only variable, but this is okay because we can initialize a read-only variable while the program is still single-threaded. The other problem is that there's a type error. We're writing a private buffer pointer into a read-only buffer pointer. So the way that Sharc deals with this is by allowing the programmer to add an explicit checked sharing cast. So the insight here is that if you have the only pointer to an object, then you're allowed to change the sharing mode of the object. So what Sharc does is it uses Heapsafe to maintain reference counts, and it checks that the reference count is 1 to make sure that you will have the only pointer at a sharing cast when you do a sharing cast. Sharc also has to null out the old pointer because it has the wrong type. So when we write something like sharing cast of temp to read only, what this actually means is that we're doing the following things atomically. We have an assertion checking that the reference count is 1. We do the assignment from temp into config, and then we null out the old pointer because it has the wrong type. So I also want to mention that Sharc can infer a lot of these annotations. And this inference is based primarily on heuristics. Yeah.
So I can see that it is safe to cast if you only have one reference, but I'm not sure that programs will always just have one reference when they wish to cast to a different sharing mode. Like,
perhaps not. In the programs we've looked at, that's been the case.
So how you said that Sharc can infer some of these operations, casting things. How's that expressed to the programmer? So like I don't write any annotations at all, and then I try to compile stuff, and then I get output that says I've inserted the following, Sharc cast into your code.
So Sharc won't add casts automatically, but it will infer some annotations based on things you've already written. So this is mainly for convenience rather than for correctness, and it's easy to override if Sharc gets it wrong. So in this case, for example, so if the programmer writes read-only here on the right side of the star, Sharc will just say, okay, well, the buffer it points to is probably also read-only. And the programmer can override that just by putting an explicit annotation here. And similarly here for temp, it's a local variable, so Sharc infers that it's private. And there's nothing to suggest that it points to anything other than a private buffer. So that annotation also defaults to private. And again, if it's wrong, the programmer can override it with an explicit annotation. So one thing that Sharc can also do for unannotated objects is we can do a thread escape analysis. So Sharc will infer that an unannotated object is in the dynamic mode if a thread escape analysis says that that object might escape. And then for objects in the dynamic mode, Sharc will check that the object is either private or read-only. So let me explain for a moment why that's needed. So here's another example in which we have a global integer variable that's only going to be touched by thread 4. And so we have a function that's run by a whole bunch of threads. And inside of this function, the thread 4 counter will get incremented only by thread 4. And E is some expression that identifies which thread is thread 4. So it might be hard to tell statically that E is only going to be true for thread 4. And if we could tell, then if we had a strong enough static analysis, we could tell that that thread 4 count is private. So Sharc will infer the dynamic mode for that variable. And so the idea here is that where the static analysis is hard, the dynamic mode allows us to do some checking to say that, okay, well, I don't know what it is statically, but maybe at runtime I can check that it's private or read-only. So here's a good point.
More detail about how you actually do that. It seems, private or read-only is not something that you normally tell at runtime, right? So you need to add extra data and so on.
Right. So we, I'll talk about that in a little bit. So far I've talked about sharing modes and the sharing cast and the dynamic mode. And so what I'm going to talk about next is a little bit about how the sharing casts work for a data structure with a bunch of different objects in it. And then I'll talk about the guarantees that Sharc is actually providing. And then I'll talk about the implementation that we did and how we've evaluated the tool. And then I'll wrap up and talk about some future directions for Ivy. So let's go back to the initialization example. But I'm going to change a little bit. Instead of initializing some global buffer, I'm going to change it so that it's initializing some linked list that's protected by a lock. So we have a list data structure and a mutex for protecting the global list head GL. And then we have a function called init. And what init does is that it allocates head of the list and passes the head of the list to some other function which initializes the list and returns us a pointer to the tail of the list or just anywhere in the middle of the list. And then what the initialization function will do is it will acquire the lock. And then what the programmer is trying to do here is cast the whole list all at once from private to locked and assign it to the global list pointer. But there's a problem here. So if Sharc, after the call to init list on the head of the list, this is what things look like. So the global list pointer might point to somewhere else. It doesn't matter. But head now points to the beginning of some list with a bunch of nodes in it, and tail points somewhere into the middle of the list. And so the intention of the programmer is to now take the global list, which is pointed to a list in the lock mode, and assign it to the list that we've just initialized privately to some thread. So if Sharc were to allow this, there'd be a problem. There's a problem here. So we have tail still thinks the thing it's pointing to is private, which is a problem because then we have one pointer pointing to that node that thinks it's locked, and another pointer pointing to that node that thinks it's private. So Sharc doesn't allow the sharing cast. In this case, we have to do something else.
Sure.
Why is it confused? I mean, is it because head and tail can potentially alias?
Yeah. Well, it's also because when you step through this list, you want to know that each node is locked, for example. So the next pointer of the node that has 9 thinks that the node that has 3 is locked, whereas the tail pointer thinks that
lock per step.
Yeah. So I'm glossing over some details here. In particular, we have some qualifier polymorphism for structure types. So if you have a locked list, then the qualifier on the head gets transferred to the qualifier on the other pointer.
Okay.
So when you do the S-cast there, if you didn't have a tail pointer, then automatically all of the next pointers also change.
Right. That's what we would like to happen.
Okay.
And so the goal now is to check that that operation is actually safe.
Right. And so when you do it, you would fail when you got to the end of the list because the reference count isn't 1.
Well, so this will fail.
Static.
If you wrote this, it would fail statically.
Static. Yeah.
Static.
Static.
Because you can't do a single object sharing mode change on a structure type that has pointers in it. You have to do a different thing.
Oh, you can't. Okay. Even if the tail pointer name didn't exist, you couldn't do it because of the structure pointers. Okay.
Right. So the way that we deal with this is with this idea called groups. So a group is a collection of objects in a C program that are identified by a distinguished group leader. For example, the head of the list or the root of a tree. And so we add this annotation to Sharc that allows the programmer to identify external pointers into a group of objects. And these external pointers have to depend on a pointer to the group leader. So we use a dependent type annotation group of G. That means this is a pointer into the group of objects whose group leader is the target of G. So for example, if we had our global linked list on the previous slide, and GL is a pointer to the head of the list, so GL is a pointer to the group leader. So GL is also an external pointer into the group. So we would annotate the type of GL by saying it's in the group identified by itself, GL. And so we also need to identify internal pointers in a data structure. And we do this with this same annotation here. So if you have a pointer in a data structure that goes into the same group, then you can just write same. So that Sharc can find the internal pointers in a group.
Can you go back? So external pointers, then if you're going to traverse it, it means that you have to have the same lock when you go in there?
The same lock. Yes.
Right. So if I'm coming in with this external pointer, then I better take the lock that is associated with the head, the leader.
Right.
Before doing anything. Okay, so external pointers, there's a little, in the dependency is a little bit like ownership in object-oriented.
Yeah. It's very similar to ownership.
But here, the idea is the data structure has these things coming from outside, maybe deep inside. That seems to be a little different. I'm just trying to understand it with respect to ownership.
Mm-hmm. Shall I continue?
Please.
Okay. So if we were to take the program and write in our group annotations, it would look like this. So we have a same annotation on the next pointer in the list data structure. We have a group annotation on external pointers into the list, in particular for the global list pointer and for the local pointers that we use in the initialization function. And then instead of a sharing cast, we're going to do a group cast, a G-cast operation. And the idea here is that we want to use our knowledge about the internal and external pointers to make sure that this operation is safe. So what we can do, and I'm only going to talk about this very briefly, and I can talk with you about it in detail offline if you're interested, is that we're going to do some use deputy-style dependent type checking of the group and same pointers. So in order to do dependent type checking for the group annotations, deputy adds in some null checks, some null pointer checks. And it turns out that the null pointer checks that deputy adds in to do its dependent type checking are sufficient to enforce the key invariant that pointers to an object agree, all pointers to an object agree on that object's sharing mode. And to reduce the annotation burden, Sharc adds in, or Sharc has a sensible set of default annotations for different situations. And also the compiler can guide the programmer to places where the default has to be overridden to get the program to type check. So now I'm going to talk about a little bit about the guarantees that Sharc actually provides. So if there aren't any compile time errors, then Sharc guarantees that private objects are only accessed by that one thread. Read-only objects aren't written, and that sharing modes agree at assignments and for argument passing. That is just basic type safety. If there aren't any runtime errors, then Sharc guarantees that there aren't any data races on dynamic objects in the dynamic mode or the barrier mode. That locked objects are always protected by the lock, the right lock, and they're not accessed unless the lock is held. And that no references with the wrong type exist after a sharing or a group cast. Sharc also guarantees that violations of the sharing strategy include the data races on a particular run of the program, except on objects that the programmer has explicitly marked racy. Also, if there's a data race between two threads running in the program, then Sharc will generate an error regardless of the thread schedule. And we also have a soundness proof that shows that Sharc actually provides these guarantees on a simplified C-like language that includes the private, locked, and dynamic modes with the group and sharing cast. So now I'll talk a little bit about the implementation. So at runtime, we do race detection for objects in the dynamic and barrier mode. So the way we do this is by keeping a big array off to the side and tracking the number of readers or a writer for every 16-byte chunk of memory. And we reset the state as appropriate when memory is allocated or freed, or when threads are spawned or die. And we also do efficient reference counting with Heapsafe to check the sharing and group casts, and this is based on an efficient concurrent reference counting algorithm. So the thread escape analysis I mentioned before is actually optional. It's an optimization. It would be safe to leave everything annotated dynamic. It would just be a bit expensive. So we do this thread escape analysis so that we can figure out that a bunch of stuff in the program is actually private, thread private. And we can also do another optimization that's very similar to, we do a flow-insensitive type qualifier analysis to restrict reference counting only to those objects that might be involved in a sharing cast or a group cast. So Sharc is implemented for C using the SIL compiler front end and about 5,500 lines of OCaml, and it's integrated into the IB compiler. So now I'll talk a little bit about how we've evaluated Sharc. So the goal here is more to investigate the runtime and programming overheads rather than to go on a bug finding mission. And so we've applied Sharc to a bunch of different programs, applications, and yes, a couple of scientific codes, and a web server, and a couple of image manipulation programs, including the GIMP. So before I give the results, I want to talk a little bit about how we actually went about applying Sharc to these programs. The way we did it was as follows. So we would compile the programs with Sharc without making any annotations, and then and with the thread escape analysis turned on, so that anything that might be touched by multiple threads in the program gets inferred to be in the dynamic mode. And then we run the program in Sharc's log and continue mode, and we inspect the error messages that get generated to see how the objects are shared in the program. And then based on the error messages and based on some hints from the program itself, like comments and variable names, we can go through and figure out what annotations and sharing casts are needed in different places. And we repeat this process until we don't get any more error messages. Is this hard to see? Yeah, so these are the results, and I want to point out a few things. First, I want to point out that we've actually got this running on some big real programs. The second thing I want to point out is that you don't really have to make very many annotations to get this idea to work. So the density of the annotations goes from being about 4 per 100 lines of code to being about 1 per 10,000 lines of code. And what we found in terms of the need for writing a bunch of annotations is that the number of annotations you need doesn't increase with program size. It increases with the complexity of the concurrency in the program. So we have a program like the GIMP where it's exploiting some embarrassing parallelism with regards to image manipulation, and so you only need 70 annotations for a program that's almost 1 million lines. But for smaller programs, which have some more complex concurrency, like the scientific benchmarks, eBarns and EM3D, you have smaller programs that need about the same number of annotations. Finally, I want to point out the runtime overhead, which are fairly low if you compare with or are competitive with existing race detectors. So to conclude, the incorrect sharing leads to data races and deadlock and some other bugs. But with a few simple annotations on types, Sharc allows a programmer to specify sharing modes for objects, but also to specify where in the program the sharing modes for the objects change. And then Sharc will check that the program actually adheres to the declared sharing strategy with a combination of static and dynamic analysis. And we've tried Sharc on a bunch of real programs and observed some manageable slowdown and memory overhead. And we've released the tool, and it's available at this URL. So there's a bunch of related work in this area. There's a bunch of work on safe C dialects and race detection, and ownership type systems are kind of related to our group's idea. There's also some Sharc-inspired work. There was a Popple paper this year that takes a fully dynamic approach and uses API calls to change sharing modes. There's also a bunch of work here at Microsoft, which it probably makes more sense for you to tell me about instead of the other way around. So now I'll talk a little bit about some future directions. So one thing I've been thinking about is using sort of Ivy-like annotations and analysis for annotating APIs and annotating, for example, if you get an object from an API, do you have to free it? Do you have to acquire or release a lock on it? Do you have to increment or decrement a reference count on it? Also, I've been thinking about extending Ivy features to higher level languages, and this would require increasing the support for polymorphism, both in Ivy in terms of type checking, but also in terms of, for example, you might need to add type qualifier arguments to templates or something like that. I've also been thinking about how to make Sharc's analysis more static, how to reduce the dependence on dynamic analysis, both to reduce the overhead, but also to improve just the static guarantees that we can make. I've also thought about applying Sharc-like techniques, type annotation, and so forth, to guide performance debugging of CUDA and OpenCL codes. And I mentioned these pessimistic atomic sections at the very beginning of the talk as one of the projects I'm working on. I think you could probably apply these to languages like Nessie that are used for embedded systems to improve support for true multithreading in those sorts of languages. That's it. Questions?
So I know you mentioned that the table earlier was part of a project not intended to find bugs, but I'm sure you must have figured out along the way whether or not you actually found any.
So there weren't. We didn't find any catastrophic bugs. So we didn't find any bugs that would cause a program to crash. We found bugs or data races that were things like, if there's a data race in this case, then a loop will execute an extra time when it didn't really have to, and all it's doing is waiting for something to happen. So there were things like that where this is really a benign race.
So do you think all the code then that you were testing through Sharc was actually catastrophically bug free, or that there's classes of bugs that your tools aren't able to catch?
So I think if we had done high coverage testing of these programs, we probably would have found a bug or two. So our approach was mostly to pick one or two inputs to the programs and make sure that we were annotating the programs to capture the concurrency that was happening for those inputs. And you can do things like okay, I've tried this input and now there aren't any more error messages, and I've got the program annotated such that I think it's correct. So let's try another input, and then you sort of do that until you're not seeing any more error messages. And that could lead you to think that you have the whole program annotated correctly, but you still might not actually be getting very good coverage. So for example, for the GIMP is a huge program. And in our benchmark, we were not doing high coverage testing. Essentially, we're exercising only some small part of the program in the test, but the annotations that we have, we think, do correctly describe the concurrency that would happen also on other runs.
Did you capture any coverage information. It'd be interesting to compare, right, the annotations with how much of that 400,000 line code that you actually covered. I mean, you might have only covered, let's say, 1,000 lines of code during runtime execution. It might be interesting to compare that to the annotation, to get a sense of the annotation burden, as well as information about, how kind of human costly those annotations were. That would be interesting to see.
Yeah, I think that would be a good metric, but I don't have those numbers.
How long did it take you from the first time you ran the tool dynamically on GIMP until you completed all the annotations? What was the length of time it took you?
It was about a week.
Okay.
So 70 annotations took a week?
Well, so so some of the annotations, one or two of the annotations were tricky. The thing that took a lot of time with the GIMP in particular was that we were doing this whole program analysis, this whole program thread escape analysis. So it would take a lot longer than, say, GCC to compile the whole program.
So it was machine effort that was taking the time, not your effort in trying to figure out the annotation?
That's right.
So the way you annotate the program is very fun, like looking at its behavior and putting in the annotations to make sure you don't get any errors. The way a programmer would use that is while the programmer is writing the application, the programmer will put annotations there. So do you have a sense of how difficult for your regular programmer it would be for adding the annotations and actually getting them right? Have you tried any kind of user study?
No, I haven't done any user study, but I would really like to see how easy this is to use for writing new code.
Can you go back to the list of programs? I don't see, why not things like MySQL or Apache kind of are multi-threaded server codes?
So for Firefox in particular, it's written in C++, and our front end only handles C. Also, I don't know off the top of my head whether it's C or C++. I think, when we were doing this validation, we basically picked one bigger program, which was the GIMP.
Two questions. So, one, if you were starting with a different language like C#, how would that affect sort of your design decisions?
So I'm not hugely familiar with C#, but I'm guessing it's sort of like Java. So I think that definitely you'd have to think about polymorphism from the very beginning of the design. Basically, in the development of Sharc for C, the support for polymorphism is almost an afterthought, or a convenience rather. But definitely for Java or C# or whatever, you'd have to be thinking about that from the very beginning. And I'm not sure exactly how that would how I would make specific changes to the design to support that.
And the second question was, my limited understanding of ownership types in these type systems is that they're fairly restrictive. That there are certain patterns of data structures that aren't well supported. So I'm wondering, in your case, are there certain types of data structures or things that, what are the limitations of your essentially ownership type system, if I can call it that? Like things that you really can't do that you'd like to be able to do. Examples like hierarchical locking, over B trees. What sort of things can't you do?
So I can't give a general characterization of what sort of data structures can and can't be handled. But for example, something even as simple as a linked list imposed on a hash table, for example, for an LRU cache replacement policy, for example, I don't think you can express with the group annotations that we have. You would want something like membership in multiple groups or something like that. And I haven't really thought that all the way through.
So the data structures in these particular applications, but were all amenable to your.
Mm-hmm.
So everything got fully annotated, all the recursive data structures, and all these things, or only if they participated in concurrent.
Only if they participated in the concurrent part of the program.